In this video, we will examine acid-catalyzed alkene addition reactions. When examining electrophilic addition reactions, it might seem that water molecules and hydroxyl groups would make good addition molecules. Each has polar bonds between oxygen and hydrogen. In each, hydrogen is partially positive because of this. It would make an ideal electrophile, attracting the attention of the alkene's double bond. The newly formed hydroxyl or oxygen ion would then make a powerful negatively charged nucleophile, which could attack the positive carbon ion electrophile in the next step. It turns out, however, that the bond between hydrogen and oxygen is too strong and interferes with hydrogen's ability to act as an electrophile and add to an alkene. This interference can be removed through the use of an acid catalyst. A catalyst is a chemical entity whose presence accelerates the reaction rate of a reaction without being used up. Chemists often write the catalyst formula above or below the reaction arrows in a chemical equation. Let's examine the acid-catalyzed addition of water to an alkene. In this reaction, we will use the diprotic sulfuric acid, whose presence in water results in the creation of hydronium ions, as you can see here. The acid-catalyzed addition reaction between propene and water works like this. Step 1. The double bond nucleophile attacks a hydrogen from a hydronium ion. Step 2. This new bond between carbon and the hydrogen ion electrophile fills hydrogen's s orbital, causing it to pass its shared electrons back to oxygen. Step 3. The lone pair on water acts as a nucleophile, attacking the carbon ion electrophile, forming a bond between the water molecule and the propyl group. Step 4. Another lone pair from a water molecule grabs the hydrogen electrophile from the electron-deficient water bound to the propyl group. This hydrogen passes its electrons back to the oxygen. Step 5. Finally, as you can see, the acid catalyst has been returned to the solution and the alcohol 2-propanol was formed during the reaction. An acid-catalyzed addition reaction between an alkene and water results in the formation of an alcohol. Now let's look at the acid-catalyzed addition of an alcohol to an alkene. Again, we will use propene with a sulfuric acid catalyst. This time the alkene will react with methanol. The addition of sulfuric acid to methanol will produce this ion. Step 1. The double bond acts as a nucleophile, attacking the hydrogen attached to the protonated methanol. As that hydrogen bonds to the propyl group, it passes its bonding electrons to oxygen. This is the slow step of the reaction. Step 2. The oxygen acts as a nucleophile, attacking the positive carbon ion electrophile. Step 3. The methanol of the solution attacks the hydrogen bound to oxygen, and it passes its electrons back to the hydroxyl oxygen. This returns the catalyst proton to the methanol solution. This reaction causes the formation of the ether 2-methoxypropane. An acid-catalyzed addition of an alcohol to an alkene causes the formation of an ether.